Now I can go a little quicker because my goal is to explain to you the difference. All we now is summarize all those important parameters and equations, initial conditions. So if we click all those stocks, converters, put the number in, put the formula in, and then the conceptual model become a mathematics model. It runs, it has a quantity. So there's three group of entities you have to understand. First, for the variables, we have 5 of them. You have the initial conditions. And for the converters, we have 2 types. One is atomic, like those birth rate, death rate, and the probabilities. And another one is deduced. Come from another formula, calculated converters. And the third is the equations, which is the flow relationship. So to understand the stellar model, you need to understand the variables, the equations, the information flow, the convert. So for the human submodel, summarize it, we have 3 variables, then we have 3 initial conditions. We assume there's 30 people. To make it easy, you can think about 30 million, 100 million, that's all up to you. Just scale up. We have one host. Is the guy have malaria? Maybe from Africa. And we have an immune group. In the beginning, none of them are immune. And we have 4 atomic parameters. The immunity rate, the probability bitten by the mosquitoes, and the probability recover, the recovery rate, how long it recover, and then the malaria-reduced death rate. That's 4. And that's all put into the interface here. And the 3 initial conditions, 4 atomic, means original parameters. For the mosquitoes, similar. We have 2 populations. We assume have 300 of uninfected mosquitoes, and there's non-vector. So we have 3 atomic parameters: the mosquito birth rate, mosquito death rate, and this shared both model. And this the mosquito bitten the human being. See, that one shared by both. And I talked about equations. We got the 3 equations for the human model that is showing here, the 3 equations, one here, and the 3rd one or the 4th one is here. That's number 4. That's the 3 equations. And actually, you can make the mosquito as 2 equations if you want. The derivative of this equals that one minus this one, and then the derivative of this one equals that one minus that one, if you want. But actually, this model we write into 4 different equations. 1, 2, 3, 4. So that 4 equations are here. Now, is the uninfected mosquito birth rate, uninfected mosquito death rate, that's 6 and 7, and the vector death rate 8, and the vector formation means the vector birth rate. That's not a birth, but they just change from the uninfected to vector 9. As I said, you can put this as 1, and this is another one, then you could make it 5 differential equations because we have 5 variables. Finally, the important one, the probability host, probability vector, and that's the two connected models. And the other two, 5 and 12, are common sense. Total mosquito equal to 2 subgroup add, total human equal to 3 subgroup add. When you put all those numbers and the equations, we have 12 equations, no, actually 10 equations, and 7 converters, 5 initial conditions. So 5 initial conditions, 7 original parameters, and 10 equations. If we write down this, the model is done. Now we simulate the model. We have 5 populations. What's the most important one? The red one, that's the human hosts. I mean the red one, yeah, is the human hosts. And the blue one is the uninfected human. Of course, we think about the human being first. In the beginning, there's all uninfected, and then more and more got infected. That's the problem. And then we look at the human host. That's the red one. In the beginning, you only got 1, but it ends up after 50 days, it peaked here. You got about 120-ish, I would guess, and then started to decrease. And then we'll also look at the vector. That's the criminal. The vector started from 0, peaked up right after 80 days, I think, and then started to decrease. There's a bunch of vectors now. Well, I'll let you discuss, but we have a little principle. What you observe from those graphs. You need to observe first, just like how do you sketch a graph in Calculus 1? Okay, you say, I need to identify the critical points. I need to identify the inflection points. I need to identify the asymptotes, which is the limit. And I need to look at the crossing points of the 2 graphs. But your job is really explain the significance to your application. So what does it mean to you? That's what we're doing. And of course, you need to look at the shape, the trend. Well, we can see it look like a logistic curve. But what about the trend? Well, here it's not very clear for you to know the trend because you only look at for 200 days. I'm not very clear so for those curves right here. So what I do? I change the 200 days to 1500 days. So that will be 4 or 5 years. So now you see the clear trend. Look at the vector. It peaked up here and started to die off. And look at the hosts. It peaked up here, pretty much flat. That's immune. The host is here. It peaked up here and then started to decrease. What's the green line? Oh, the uninfected population. And in the beginning, they're all uninfected. They almost wiped, they're all infected, all uninfected again. So, in other words, you can see after 5 years, the disease, the malaria is kind of under control, or the people just died. So anyway, I will let you do the discussion yourself by run the different models, and you can always put if, and analyze the model. If you change the initial condition, if you change the probability, especially two probabilities. First is the probability the mosquito bite human, and the second, the probability the mosquito is a vector, and that's not original, and the probability the human is a host. Or if you can quarantine the hosts, you don't have the problem. So there's all different way you can find different strategies you can find from the model to help you to get an idea. Is that number true? No. But does the model give you the insight to how to deal with the disease? The answer is definitely yes. You got hundreds of thousands of scientists are doing the job. But we just learn how to use the math to help you to deal with the disease spread problem. Okay, that concludes all our biology applications for this mathematics modeling course. And I hope you really learn by doing, and the project that you're going to do will make the real difference for you to command this master key to solve problems by using the computational tools, mathematics, and of course, the system engineer procedures. Thank you for your participation. I really enjoy this module. I hope you can do a wonderful project and also enjoy the project and teamwork. I will see you next time.